Hello, I'm SA, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
Rudolf Clausius, with his 860 treatise on the mechanical theory of heat, stands as a monumental achievement in the development of thermodynamics, solidifying the discipline's foundations and fundamentally altering our comprehension of energy, entropy, and the behavior of heat. This work, a refinement and expansion of his earlier publications, provided a clearer, more cohesive, and mathematically rigorous formulation of the first and second laws of thermodynamics, setting the stage for future advancements in statistical mechanics and related fields. Clausius synthesized disparate observations and theoretical constructs into a structured framework. The intellectual landscape prior to Clausius' 1860 paper was a patchwork of experimental findings and nascent theoretical explanations regarding the nature of heat. Carnot's work in 1824, Reflections on the Motive Power of Fire, although groundbreaking in its analysis of ideal heat engines, relied on the caloric theory of heat, a now antiquated concept that treated heat as a conserved fluid. James Prescott Joule's experiments in the 1840s, demonstrating the mechanical equivalent of heat, challenged the caloric theory, yet lacked a comprehensive theoretical framework to fully displace it. Similarly, Julius Robert von Mayer also contributed significantly to establishing the equivalence of heat and work. Hermann von Helmholtz's 1847 treatise on the conservation of force presented a broad statement of energy conservation, but it required significant refinement to be specifically applied to thermodynamic systems. Clausius, building upon these predecessors, sought to reconcile Carnot's insights with the principle of energy conservation, thereby resolving a crucial tension in the understanding of heat. And Clausius' 1860 paper achieves several key objectives. First, it formally articulates the first law of thermodynamics, expressing it as a mathematical relationship between the change in internal energy of a system, the heat added to the system, and the work done by the system. This relationship is expressed as the change in internal energy represented as du equals dq, representing the heat added, minus dw, representing the work done, u equals dq minus dw. While the principle of energy conservation had been proposed previously, Clausius' formulation provided a precise and usable form for thermodynamic analysis. The paper emphasizes that internal energy is a state function, meaning its change depends solely on the initial and final states of the system, irrespective of the path taken. Second, Clausius provides a more refined statement of the second law of thermodynamics. He introduces the concept of entropy, a measure of the disorder or randomness of a system, and postulates that the total entropy of an isolated system can only increase over time or remain constant in a reversible process. Mathematically, Clausius expressed this as ds is greater than or equal to dq divided by t, where ds represents the change in entropy, dq represents the heat transferred, and t represents the absolute temperature. ds is greater than or equal to dq divided by t. This inequality, now known as the Clausius inequality, provides a fundamental criterion for determining the spontaneity of thermodynamic processes. Third, the paper clarifies the relationship between the microscopic behavior of molecules and the macroscopic properties of thermodynamic systems. Although Clausius did not develop a full-fledged statistical mechanical theory as Boltzmann later would, he recognized that heat involved the motion of molecules and their temperature was related to their average kinetic energy. This perspective paved the way for the development of statistical mechanics, which provides a microscopic foundation for thermodynamics. A direct application of Clausius' work was the improved design and analysis of heat engines. By applying the first and second laws of thermodynamics, engineers could calculate the maximum theoretical efficiency of an engine operating between two given temperatures, represented as 1 minus the ratio of the cold reservoir temperature to the hot reservoir temperature. This is expressed as 1 minus T sub cold divided by T sub hot. This understanding allowed them to optimize engine designs to approach this theoretical limit, leading to increased efficiency and performance. Clausius' work also had a significant impact on the development of refrigeration technology. The principle of refrigeration relies on reversing the operation of a heat engine, using work to transfer heat from a cold reservoir to a hot reservoir. Clausius' thermodynamic analysis provided a theoretical basis for understanding and improving refrigeration cycles, leading to more efficient and effective refrigeration systems. Clausius' 1860 work laid the groundwork for subsequent advances in thermodynamics and statistical mechanics. James Clerk Maxwell, deeply influenced by Clausius' work, developed the Maxwell distribution of molecular velocities, which describes the distribution of speeds of molecules in a gas at a given temperature. This distribution is now called the Maxwell-Boltzmann distribution. Ludwig Boltzmann, drawing upon Clausius' concept of entropy, formulated the Boltzmann equation, which relates the entropy of a system to the number of possible microscopic arrangements, or microstates, corresponding to a given macroscopic state. This relationship is expressed as S equals K sub B times the natural logarithm of omega, where S represents the entropy, K sub B represents the Boltzmann constant, and omega represents the number of microstates. S equals K sub B times the natural logarithm of omega. Boltzmann's work provided a statistical interpretation of the second law of thermodynamics, showing that the increase in entropy is associated with the tendency of systems to evolve towards states of higher probability. Josiah Willard Gibbs extended Clausius' work to the study of chemical thermodynamics, developing the concept of chemical potential and applying thermodynamic principles to the analysis of chemical reactions and phase equilibria. Gibbs' work provided a comprehensive framework for understanding chemical systems and laid the foundation for chemical engineering. The reception of Clausius' work was initially mixed. While some scientists quickly recognized its importance, others found his ideas difficult to grasp or were resistant to the abandonment of the caloric theory. One particular area of controversy revolved around the interpretation of entropy. Some physicists, accustomed to thinking in terms of conserved quantities, struggled with the concept of a quantity that always increases in isolated systems. This initial resistance gradually diminished as the power and generality of Clausius' approach became increasingly evident. The development of statistical mechanics by Maxwell and Boltzmann provided a deeper understanding of entropy, resolving many of the initial concerns. Clausius' work was directly influenced by Carnot's analysis of heat engines, Joule's experiments on the mechanical equivalent of heat, and Helmholtz's statement of energy conservation. Carnot's work provided the starting point for Clausius' analysis, although Clausius rejected Carnot's reliance on the caloric theory, recognizing the importance of Joule's experimental findings. Helmholtz's work provided a broader context for understanding energy conservation, but Clausius' contribution was to specifically apply this principle to thermodynamic systems and to develop the concept of entropy. Clausius' 1860 paper directly influenced Maxwell's work on the distribution of molecular velocities, Boltzmann's development of statistical mechanics, and Gibbs' contributions to chemical thermodynamics. Maxwell explicitly acknowledged Clausius' influence in his papers on the kinetic theory of gases. Boltzmann built directly upon Clausius' concept of entropy, providing a statistical interpretation of the second law. Gibbs extended Clausius' thermodynamic framework to the study of chemical systems, developing new concepts and tools for analyzing chemical phenomena. These subsequent works solidified Clausius' legacy as one of the founders of modern thermodynamics. A subtle element of irony underlies the initial reception of Clausius' groundbreaking ideas, a concept so crucial to understanding the directionality of natural processes. Entropy initially instilled a sense of unease among some scientists. This hesitation stemmed partly from a prevailing inclination towards deterministic views of the universe, where everything is conserved. The notion of a quantity that inexorably increased, implying a kind of ultimate heat death of the universe, presented a counterintuitive challenge to that deterministic worldview. Beyond its immediate scientific impact, Clausius' work has had profound implications for our understanding of the universe and our place within it. The second law of thermodynamics, as formulated by Clausius, dictates that the universe is constantly evolving towards a state of higher entropy, or greater disorder. This has implications for the ultimate fate of the universe. The concept of entropy has also found applications in diverse fields, including information theory, ecology, and economics. In information theory, entropy is used to measure the uncertainty or randomness of a message. In ecology, entropy is used to study the flow of energy and matter through ecosystems. In economics, entropy is used to analyze the efficiency of resource allocation. In conclusion, Rudolf Clausius' 1860 paper on the mechanical theory of heat represents a pivotal moment in the history of science. It provided a clear, rigorous, and mathematically grounded formulation of the first and second laws of thermodynamics, introducing the concept of entropy and paving the way for the development of statistical mechanics. His insights not only revolutionized our understanding of heat, energy, and the behavior of matter, but also laid the foundation for a wide range of technological advancements and continue to shape our understanding of the universe today. The legacy endures and will continue to shape scientific thought.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, Please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.